This video is to show you that within the Poisson you will find the binomial distribution embedded there. So what we're going to do is we're also going to make use to understand this relationship of this nifty relationship right here. As n goes to infinity, 1 plus 1 over n to the n is equal to e, or 2.71. So let's get to this relationship first and understand that because, well, that's not only important for understanding the relationship between Poisson and binomial, but also important for simply understanding compound interest. So let's say that we wanted to borrow $1, or we had a principal of $1, and we wanted to borrow that $1 at 100% interest. What would we pay after 1 year? Well, we'd pay the $1 principal plus the $1 of interest. So that would be $2, right? So that would make a loan shark very proud. So that's our interest, and there's our principal right here. But what if we decided we didn't want to wait for a year? What if we only did it for 6 months? For 6 months, we would have $1, and then we would pay, what, only 50 cents, right? So it'd be $1.50 for 6 months. So, but what if we then charged another 50% for the second 6 months on the off chance I decided I wanted to continue after all? So let's say we went our 6 months and then I decided I'm going to keep going. So my new principal is going to be $1.50, and I'll pay for the second 6 months half of that, so it's 75 cents. So then I get to $2.25. So if I have this option to pay earlier, my annual rate looks more like 125% annual interest or annual rate. So you agree to this. It's called compound interest. You can pay me back after 6 months, or you can reborrow it for another 6 months. What if I have the money in 1 month? Well, if that's the case, I'll charge you what? So 1 month would be 8.5% in a month, right? So then we could say our original principal would be 1 plus 0.085. So it's 1.085. And in another month, I would have something like 1.085 squared, right? That's the second month. And then in a third month, it'd be 1.085 to the third. So after 1 year, I'd have 1.085 to the 12th power. So that would be $2.66. So that's a 166% effective interest, just for that ability to stop and then extend if I wanted to. What about a per day charge? Per day, I'd get, well, 100% divided by 365. That would be if I compounded every day. It'd be 1.027%. That's compounding every day. And so then that ends up with something like 1.00274, right? Raised to the 365th power, which is 2.7148. Okay, well, we can do that, but what if we can get more granular. What if we decided to do hourly compounding? Well, then we'd have what, 100% over 8,760. That's how many hours in a year. And that's 0.01147 per hour. So we could say then that 1.000114 raised to the 8,760th power, right, that's the raising to that power, is 2.714433. So what we've got in essence is we've got some kind of principle, and we say it's 1 over 100% divided by n, however big we want that n to be to get it more granular. And we work that out for, here's the principle, was the $1. 1 to the 1 was $2, and when we worked it out with 12, it was $2.613, and when we worked it out with 1 over 365, it was 2.71, and indeed, as it turns out, as n gets ever larger, this number right here is going to approach e. So in other words, the limit as n goes to infinity of 1 plus 1 over n to the n is just e, which is 2.71 and a whole bunch of extra things. So we just showed our first result. Now let's say that you're a traffic engineer and you've got to figure out how many cars are going to pass in an hour. So first thing you do is you define a random variable, and that is going to be x, and that will be the number of cars that pass in an hour. So you want to try and figure out the probability distribution of this random variable. So once you get that, you can calculate all sorts of things. First thing we'll do is we'll assume that any hour is the same as any other hour, even though that's probably false. After all, we've got rush hour and so forth. But even within the hour, let's say that there's no differentiation. So the first thing you do, and you're going to do this for any distribution, is you're going to figure out what the mean is. So what you'll do is you'll sit on the curb and you watch passing cars over a bunch of hours. And so what you'll come up with is some mean. We're going to call it lambda. And so for our case, maybe we'll find it's like 9 cars in an hour. And we've sat there for hundreds of hours watching, and that's what we found. Now, the binomial distribution says that the expected value, lambda, is equal to the number of trials we have times p, which is the probability of success. And in what we've seen previously is that's like in each toss. So we can say lambda cars per hour is kind of like saying, well, our n is, we've got 60 minutes in an hour, and that's like saying we've got 60 trials. N is equal to 60 trials. And then we've got our p, and that is lambda over 60 cars per minute. So that is like our p right there, probability. So now we can say the probability that x is equal to, I don't know, some number. We're going to call it, I don't know, maybe it's 3, something like that, is going to be equal to 60, choose k, we might have like 3 cars, times lambda over 60 to the k, right? And that's how many successes we'd have. And again, this is binomial. And 1 minus lambda over 60 minus k, right? And this is our probability of failure during that time, or during that trial. But couldn't it happen that we could have more than one car passing in a minute? Right now, if we had something like 5 cars passing in 1 minute, it would count as a success. So we can solve that by getting a little bit more granular. Okay, so we're going to now have something like, instead of 60 minutes, let's say how many seconds in an hour. So we've got now lambda 3600 raised to the k, and then now it's 1 minus lambda over 3600 minus k. So we've got a little bit better approximation, and this one is again saying that k cars pass in those 3600 seconds. And this thing right here is the probability, I'm going to write this up here just so you have it, probability that a car passes in any given second. And this obviously is that a car didn't pass in that given second. But still, we've gotten more granular here, but 2 cars could come by in like half a second. So now what do? Well, basically, we're going to need to get more and more granular so that we can end up with the Poisson distribution. The Poisson is really just the binomial. It comes from the common sense flipping of coins. So we're going to need one more little math tool, the limit as x goes to infinity of 1 plus a over x raised to the x is just e to the a, right? So that's very close to what we showed before. If you want to prove it, you can say saying 1 over n is equal to a over x, and x is equal to na, and the limit as x approaches infinity, n does 2. So this is the same as the limit as n goes to infinity of 1 over 1 plus n to the na, and that's the limit as n goes to infinity of, I'm going to put 2 brackets here, 1 plus 1 over n to the n, and then all of that raised to the a, and then that becomes the limit as n goes to infinity of 1 plus 1 over n c to the a is e to the a. So now do you believe me? This, as it turns out, is exactly how we got to e, of course. There's another tool we need, and that is simply that x factorial over x minus k factorial is x over 1 times x minus 1 over 2 times x minus 2 over 3 times x minus k plus 1 over the kth term. So if we had something like 7 factorial over 7 minus 2 factorial, then we have 7 times 6 times 5 times 4 times 3 times 2 times 1. We've seen this kind of thing before. Times 5 times 4 times 3 times 2 times 1. Whoops. And we start crossing things out, and all we're left is 7 times 6. So there we go. We have all the tools that we need right now. So we'll say e to the x, the expected value of x is lambda, that's success in an hour, is equal to n times p, and that n is actually successes in a much smaller interval. And what is this p? It's actually the probability of successes in a much smaller interval. So we had previously said that, well, first n was a minute, and p was a probability of success in a minute. Then we said n was a second, and then the p was a probability of success in a second. And if we let n go to infinity, what sort of formula falls out for us? If we describe this as the binomial distribution and let n go to infinity, here's what happens. The probability that x is some k. So let's say that we get 3 cars in a particular hour. We can let the limit as n goes to infinity of n choose k, and that means k moments in time as n approaches infinity. Let's see, so say the probability of success, which is, well, I'm going to write this all out. Probability of success, and that probability is lambda over n raised to the k. That's the probability that we have k successes, and then it's 1 minus lambda over n to the n minus k, and this is the failures, right? So this is the p part right there, which is lambda over n raised to the k. And as those, so I'm going to erase this p right there. We know that that's what it is. It's like this is the p, probability of success. This is the q, probability of failure. And I'm going to write this down so it's very clear. I'm going to say we've got k moments in time as n approaches. Should have just written an arrow there. Approaches infinity. The intervals n becomes super duper small, and we have an infinite number of moments. That's the n, and only k of those moments are successful. So we might say k was 3, then we've had 3 times where we've had a success, a total of 3 cars passed. Now let's do some substitution. First we're going to make things very clear. We'll say the limit as n goes to infinity of n factorial over k factorial times n minus k factorial, right? Because that's just what we had seen before. Let's go back. Right there, there's our n choose k. So, okay, so there's our n choose k. We've written it out there clearly. And next we'll say what we had in the remainder of that expression. So we've got lambda raised to the k over n to the k. So let's go back. So that's lambda to the k over n to the k, right? You see right in here. And then we're going to write the rest of it, and that's going to be 1 minus lambda over n to the n times 1 minus lambda over n to the minus k. I just broke things up there. Okay, I'm taking this part in red right here, and we're going to write that as the limit as n goes to infinity of, well, let's see, n is going to be n times n minus 1 times n minus 2 times n minus k plus 1. So if you count them, there's 1, 2, 3, well, k terms altogether. And the lower part right here, we can break that up. Well, let me circle. So it's actually, this red part here is the same as this red part right here, because that's what's left. So now we still have this part and this part. So first let's write the n to the k downstairs here. We'll just keep it right there. And then we're going to come over here and we'll say we've got the lambda k, lambda to the k, over, well, we've got a k factorial right there. So it's k factorial and we brought that n to the k down here. So we've got this part, and now we can say we've still got our leftover parenthetic expressions. 1 minus lambda over n to the n, and 1 minus lambda to the n to the minus k. So let's just keep in mind a few little tricks from the calculus. The limit as x goes to a of f of x g of x is just the limit as x goes to a of f of x times the limit as x goes to a of g of x. That's our little side note right there. So we'll just keep that in mind. So in other words, the limit as n goes to infinity, well, let's see, the largest term is n to the k on top, right? Because if you look at the n, we've got k terms, so it's going to be an n to the k on top. And we've also got an n to the k on the bottom. So, well, what does that mean? We've got something like 1 plus 1 over n, etc., right, when you carry everything all out here. And so, divided by 1, and all of this will become 1 in the limit. Okay, so now we've still got all the rest of this stuff. So let's see, we're going to put that as lambda to the k over k factorial. We'll keep that as it is. And then this part is going to be, right, the limit as n goes to infinity of 1 minus lambda over n to the n, and then times 1 minus lambda over n to the minus k. So this one right here, I'm going to circle that in red, this right here, in the limit as n goes to infinity becomes e to the minus lambda. And then this one right here, as n goes to infinity, this will go to 1, right? And remember, keep in mind that the limit of n to infinity, as n goes to infinity, of 1 plus a over n to the n is just e to the a. So now we're going to take all of these results and we'll say, well, the first part here, this first whole expression we just showed going down here, it's just 1. And then the second part is this right here, right? So we'll put that there. That's lambda to the k over k factorial. And then the third part is e to the minus lambda, and the fourth part is 1. So what does this all bring us to then? It says that in essence, and remember we're dealing with a t that's 1 hour right here. So we'll just say the probability that x is some k, like 3 cars, is the limit as n goes to infinity of n choose k lambda over n k 1 minus lambda over n to the minus k is just lambda to the k e to the minus lambda, again that t is an hour, all over, a little squished in here, k factorial. So you don't initially see this binomial theorem, but it is indeed buried there. So let's say that we had lambda is equal to 9 cars passing in an hour. Pass in an hour. and our. So then we can say the probability that x is 2 is just going to be 9 squared over 2 factorial e to the minus 9, 81 over 2 times e to the minus 9. There's our probability using the Poisson. Okay, one last little point. Can Poisson apply to space as well as time? Of course it can. So let's say that we have a random variable, and that random variable is the length from any starting point on a wire until a flaw is detected. So for example, the distance to the first flaw exceeds 3 millimeters if and only if there are no flaws within a length of 3 millimeters. So then the probability that x is greater than some set x, that's kind of like our k that we've been using before, is the probability that you've got no flaws, n is equal to 0. And so then we can say it's something like plugging in to Poisson e to the minus lambda x is 0, no flaws, and 0 factorial, and that is e to the minus lambda x. So then that cumulative distribution function is just the probability that x is less than or equal to x, whatever that k is actually, is equal to 1 minus e to the minus lambda x, where x is greater than or equal to 0. That's just the cumulative distribution function of x. And then the probability density function of x is just going to be f of x is equal to lambda e to the minus lambda x, and that's our exponential random variable. So again, this is the random variable x right there that equals, when I say there, I mean right here, that equals the distance between the successive events of a Poisson process with a mean number of events lambda per unit interval is described by this equation.